All right, we're going to go through the shell notes, and you're just going to listen to the video lecture and fill your notes in as we go, and I will check to make sure that this is done when I see you guys again next week. So forces, we've been talking about forces a little bit so far, but we really are going to get into the detail of this. We've been talking a lot about forces when we talk about work, but we're just going to look at that from a different perspective. So force basically is any push or pull exerted on an object. So that's how we can recognize them. Details about forces, we've already studied. The unit for force is a Newton. So just a little bit of review. It's always kind of nice that not everything is new. So capital letter N is what we're going to use for newtons. But we need to get more into this detail. So it's important in physics when we make measurements to recognize whether things are what we call a vector quantity or a scalar quantity. So a force is a vector quantity. Force is an example of that. It's a quantity that needs both magnitude and direction for a complete description. Well, what does that mean? So the magnitude basically talks about the strength of an object. So basically the number value. Is it 30 or 40 or 50 newtons? And the direction we get is, am I being pushed or pulled left or right? So when we describe the push or pull, we need to know how strong it is and in what direction, okay? Just for completeness, a scalar quantity is only described by its magnitude. So again, the strength or the numerical value, it has no direction associated with that. So examples of scalar quantities would be time. So we say time is like 3 hours or 4 hours. That gives us the magnitude. But there is no direction associated with time. We wouldn't say 4 hours to the right or 4 hours up. That doesn't make sense. Another example that we have used already is mass. So we measure mass in kilograms. This is also a scalar quantity. So the mass of an object, 3 kilograms, 4 kilograms, that's the magnitude. But you wouldn't say 3 kilograms up or anything like that. So how are we going to draw them? Because we're going to be drawing a lot of pictures with forces. Forces are represented by arrows, just like that. And the length of the arrow gives us the magnitude or the strength. So for example, if I had an arrow and I labeled it 5 newtons, if I was to draw an arrow that was 10 newtons, it would be essentially twice as long. So the length of that arrow is what gives us the direction, and the arrowhead is what's going to give us the direction piece. So the length of the arrow is the magnitude. The arrowhead is going to point in the direction that it's acting. So that's going to be important when we start introducing the forces. So what is a force also? More technically, we know it's any kind of push or pull, but more importantly, it's an interaction. And that's a big word. Between two things or systems or something, but we call these two things the object, which is usually a thing you're interested in, and the agent. So we're going to define these, and it's really important for us to understand this idea of the interaction between two things. So the object is really what feels the force. We call it the feeler. That's kind of a funny way to refer to it, but essentially that is going to feel the force. The forces are acting on it. Feels the force. And the agent, kind of the funny word to think of the agent, is the dealer. So we talk about the object agent as being the feeler and the dealer. The dealer is the one that gives the force or provides the force. So when we see the feeler and the dealer together, that's what we mean by an interaction. So if I touch something, it's going to touch me back. So let's see if I can draw a really cool finger here. I'm not a super great artist here. Yeah, that doesn't look, it looks like a hand with a really big finger there. All right, if I push on the box, oh, that's just a terrible picture. Let's try something else. How about a ball? A ball, much better. A ball kind of travels towards a wall and bounces off. So when the ball hits the wall, there's an interaction between the ball and the wall. That's a much better picture. So the ball is going to get pushed to the left when it hits, and the ball is going to push on the wall to the right. So again, that's what we mean by an interaction, a feeler or a dealer between that. So if we were just interested in the ball, we would say the wall pushes the ball to the left. That's how that would look as far as describing the forces. All right, So we need to describe the different types of forces that we're going to have here. And we need to start to, the more we use it, the better we'll get at memorizing them. So the first kind of group of forces is the contact forces. A contact force means you can see the dealer of the force. You actually see it touching. So you will see a contact. So the ball hitting the wall, you can actually see that actually happens. That was what we would mean by a contact force. So something is touching. There's a touching that can be observed. And I'll give an example of a non-contact force that we'll come back to a little bit later. Switch colors back. So the first one is called the normal force. And it's normal doesn't mean that it's not strange. Normal is kind of a math term that means perpendicular. And that gives us a sense of the direction of the force. But basically the definition of a normal force, all right, so that's a little bit more about direction, is a support force. So this is what holds things up. So a table. So if you look at our picture here, this table, this box is sitting on a table here. That table is providing a normal force on that box. It's holding it up. So the direction of this force, if this is my object that I'm interested in, it's going to have a force that's pushing it up, and I'm going to label it the normal force. So the normal force, we either use a capital letter N or force with a little subscript N. So we have to be careful with this one because we don't want to confuse it with a Newton, which is a unit, and this is a variable. So I'm just going to label it F sub N so we don't get confused at all by it. So this support force, so if my object is the box, right? That's the feeler of the force. The dealer of the force, or the agent, would be the table. So our interaction is box and table. The box is pushing on the table is pushing back on the box. The agent of the support force in this case is the surface that it's sitting on. So it could be a table or a ramp or anything like that. And then the direction, as I mentioned, is always going to be 90 degrees to the surface. And that's what the definition of perpendicular is, if you haven't run into that in a math class. So notice how I tried to make it a 90-degree angle between the surface. All right, moving on, the tension force. This is a force that's due to a string or a rope or anything like that. Tension force, we're going to use FT. Sometimes we'll use a big T, and I know it's less writing, but I think we'll try to stick with FT. The agent of that force is going to be the rope or string. And the direction is always away from the object, away from, and along the string. So if I were to draw this, I would draw it kind of on the box, and it's going to be along the string with an arrowhead, and that would be my force tension. So it's kind of touching the box and along the string. Okay, the third one that we're doing is the force of friction. So friction is a resistive force. The variable we're going to use is a lowercase f, and again, this is also a surface force. This resistive force is between two solid objects. So, and the direction is always going to be opposite the motion. So if this box is moving this way, our friction force would be opposite. That's what we mean by resisting, and that would be our frictional force. Applied force is kind of a catch-all. It's any push or pull. Usually it's like a person or something like that. And we'll just call it big F for that. So if a man pushes the box to the right, that push force would be to the right. Air resistance or drag, this is also resistive force, but it's due to a gas or liquid. And we'll call it just kind of the force of the air. The agent in this case is going to be the gas or liquid. And again, it's going to resist motion. So if my rocket is moving this way, this is the motion, the drag force or the air resistance force would be opposite. All right, the last force, and this is the end of the lecture, are what we call non-contact forces, so you can't see something touching it. And the most common example is the force of gravity. So we've already been talking about this one. You can't see anything pulling on it when something falls to the ground, but we know that it exists. And we've used Fg for force of gravity, or W for weight. So that's the other name that the force of gravity goes by. And the agent is going to be the Earth, or the Earth's field. And the direction is always going to be straight down, towards the center of the planet. So if I'm hovering over the planet, straight down, these would be gravitational forces. Even if I was parked on an incline, gravity would always act straight down, and that would be the force. All right, so that finishes the catalog of forces, and you can go on to the next part of the assignment.